All right, here's a first problem. Let's convert to cycle notation. So here's a permutation. The first thing you need to be wary of is that if you don't see any parentheses, this means that this is one-line notation. So the other way to think about this is the old-fashioned x, f of x charts that we're used to seeing in high school, the xy tables, only we just chosen not to write down the x table at all. We're just writing down the y table because it's already understood that the x table is just going to be the numbers 1 through n in increasing order. That's what one-line notation is. So that tells you, what is sigma of 5? It's 1. What entry's in the fifth place? It's 1. So that doesn't tell you how to convert to cycle notation, though. That's just pointing out this isn't already in cycle notation. This is not a one cycle. It is not the case that sigma of 1 is 3. Why? Because we see sigma of 1 is supposed to be 2. Cycle notation is always indicated by showing parentheses somewhere. Even when it's a one cycle, we always write the parentheses. Why? Because one-line notation also exists, so we always want to communicate to the reader which notation we're using. All right, that misconception aside, how do we actually do the conversion? Well, we pick an element, let's say 1. We figure out what the permutation does to 1. 1 is our x-coordinate. What is our y-coordinate? It is 2. Congratulations, that's the first step. So now we want to figure out what the permutation does to 2. So each of these cases, we're starting with an x-coordinate, figuring out the corresponding y-coordinate, and then writing that next. Now we're going to treat the number you just wrote down as an x-coordinate. So now 2 is our x-coordinate. What is the y-coordinate for that? So what's sigma of 2? It is 4. One more down. So there's 4 as a y-coordinate. Now what happens when 4 is an x-coordinate? What is the corresponding y-coordinate? It is 8. All right then. What happens when x is 8? Well, sigma of x is 7. What happens when sigma of x is 7? X is 7, sigma of x is 5. What happens when x is 5? Sigma of x is 1. And there we finally get back to one of our cycles. So this closes off a cycle. So we always think of ourselves, each of these cases when you're going one step to the right is an sigma x pair. So when you take any two of these, you're getting an xy coordinate. But then that y-coordinate is also the x-coordinate for another xy pair, which is strange to think about, but that's because we're not used to thinking about permutations. We're used to thinking about real-valued functions, and most real-valued functions are not bijections. But when you have bijections of finite sets, this type of idea actually makes sense. If everyone in a race comes in some place in the race and there's no ties, then everyone has a specific position and a specific name, and this type of idea works. Are we finished? Well, our permutations of 9 symbols, we have 6 numbers appearing. Something's missing. Let's pick the smallest thing that's missing. I see that 3 is missing. So let's start a new cycle involving 3. We know 3 belongs on some cycle, so let's figure out what else is on that cycle. What does sigma do to 3? It sends it to 6. What does sigma do to 6? It sends it back to 3. And then finally we see that 9 is sent to itself. So there is our answer. Okay, so here's a problem. Let's compute the product. So what do I mean by that? That means these are each permutations. So technically we are multiplying them together, and we want to rewrite it into a cycle notation where the cycles are disjoint. We see that these two cycles have an element in common. These two cycles have an element in common, so it's not disjoint. So one approach could be to multiply them 2 at a time and use associativity, or the other one is to use an algorithm we've been developing. We know this is a permutation, so we just figure out the cycle type of the resulting permutation by figuring out where 1 goes, where 2 goes, and so on. So let's figure out what this permutation does to 1. So here's 1. Remember, composition always goes from right to left, so we need to start all the way at the right and work our way left. So the idea is you start with the number at the right, you're viewing it as the input here, and you're going to keep working till you get a number popping out all the way at the left. Now whatever number we get all the way at the left is going to be the number we write here. So we read from left to right, we see that a 1 appears in the first cycle. And we ask ourselves, what does this first cycle do to 1? Well, it sends it to 3. And so the first permutation on the right sends 1 to 3. Ergo, 1 goes in and 3 comes out. So it is not the case that this means that our permutation sends 1 to 3, because there's other cycles going on that have 3 in them, so we have to do more work. So 3, what does this permutation here, this transposition, do to the number 3? Well, 3 doesn't appear, so it leaves 3 alone. So you can view that as 3 goes into this cycle and comes out unchanged. If you have all the students in a classroom across the hall stand up and rearrange desks, that doesn't do anything to any of the desks in your class. All right, let's consider what this permutation does to 3. Well, 3 appears on this cycle. It appears right here. So there's our 3. What does this cycle do to 3? Well, it's at the end of the cycle, so it has to cycle back to the beginning. 3 gets sent to 1. So 3 goes in, 1 comes out. So we see 3 goes in, 1 comes out. Again, the answer is not 1 because we're not all the way to the left yet. So we still have to see what this last cycle does to the number 1. And 1 does appear. So we see 1 appears on this final leftmost cycle, and the cycle sends 1 to 2, so 1 goes in and 2 goes out. And so we see 1 got sent to 3, which got left alone, then 3 got sent to 1, and then 1 got sent to 2. So when you do all these cycles one after the other in that order, 1 becomes 2. Ergo, our permutation so far in cycle notation, disjoint cycle notation, is 1, 2, open parenthesis. Another common error would be to put a closed parenthesis here, but we don't know that for sure. That would only be true if you put 2 in on the left-hand side and end up with 2 on the right-hand side and end up with 1 on the left-hand side. In other words, when you put 2 as the input to your permutation, you get 1 as the output. We don't know that yet. We need to check and see what actually happens. Instead, the only thing we can say for sure right now is that we have open parenthesis 1, 2. that's not a finished answer. It's a work in progress. So to finish the cycle, we got to figure out what the permutation does to 2. So let's put 2 in as the input to this machine. We put 2 in on the right. 2 appears in the first cycle, so we got to figure out what the cycle does to 2. It sends it to 4. So we see that 2 goes in and 4 walks out. Now we got to see what happens when you put 4 into this cycle. Well, 4 appears here, and it's at the end of the cycle, so it gets sent back to the beginning. 4 becomes 2. So we see that 4 goes into this cycle and 2 comes out. We're not done yet because we're not all the way to the left. So we need to put 2 into this cycle. Well, 2 doesn't appear at all, so 2 goes in and 2 comes back out. So that got left alone. Finally, we need to put 2 into this last cycle. It appears here. 2 gets sent to 3. So finally, we see 2 goes in, 3 comes out. So overall, the first cycle sent 2 to 4. The second cycle sent 4 to 2. The third cycle fixed 2. And the last cycle sent 2 to 3. And so finally, we see that 2 got sent to 3. Now, let's see what happens with 3 as the input. So 3 appears in the first cycle. It gets sent to 2. So 3 goes in, 2 comes out. Then we put 2 into the next cycle. It appears there on the left. So 2 is sent to 4 on the next cycle. So 2 goes in, 4 comes out. 4 doesn't appear on this cycle here at all. So 4 comes back out. 4 appears at the very end here. And so cycles wrap around, we are sent to 1. So 3 is sent to 1. But 1 was at the beginning of our cycle. So now, at long last, we can close off the cycle. And so there's one of the cycles in our permutation. And you can check then that the other cycle would have to be 4 by itself. You can check that. 4 gets sent to 1, so 4 goes in, 1 comes out. 1 gets sent to 3, and then 3 gets sent to 4. So sanity check, the answer's right. So this is the answer. So yes, this is a third approach for doing this. You can obviously see the disadvantage of this approach. It requires copying down your product multiple times because you have to write down these numbers multiple times. Either that or you have to get the eraser ready to erase constantly. With practice, you get good at doing this in your head. Now I'm going to do a harder example. Let's do this product. Now there's actual powers involved. First, it's worth pointing out that inverse can always be rewritten as a permutation in the reverse order. And another approach is that squaring is the same thing as multiplying a permutation by itself. So there are 2 approaches to solving this problem. The first approach would be to write down that square like this. And just now accept the fact that you're computing a product with 4 cycles involved. That's approach 1. Or Our method 2 is to go ahead and use skip counting to compute the square. So what do I mean by that? Well, I mean 1 goes to 2, but if you're squaring it, so let me state it this way. If sigma is this permutation, then what's sigma squared of 1? Well, it's sigma of 1. What's sigma of 1? It's 2. What's sigma of 2? It's 3. So what I mean by skip counting is because you're squaring, instead of taking an element in the cycle and going 1 to the right, you're going 2 to the right. So 1 goes to 3. Instead of going 1 to the right, you're going 2 to the right. 3 goes to 4, goes back to 1. Similarly, 2 goes going right twice, 2 goes to 4. Going right twice, 4 goes to 1, goes to 2. It closes off. So this right here is the square. So that's another way to compute the square. So it's up to you. I think the advantage of this approach is that this expression is simpler than this one, but there's nothing to stop you from doing it the harder way. That being said, I am of course going to use the easy route. So 1. Doesn't appear in the first cycle, so it comes out. Doesn't appear in the second cycle, so it comes out. Finally appears in this third cycle, so 1 becomes 3. Finally appears in this cycle, so it becomes 4. So I put in 1 on the right, I get 4 all the way on the left. 1 is sent to 4. So there's that answer so far, but we're not done yet. We got to figure out what happens to all the other numbers, right? So what happens to 4? 4 appears here and is sent to 3, so 4 becomes 3. 3 does not appear in this cycle. Three becomes 1. 1 does not appear in this cycle. So we see that 4 is sent to 1. All right then. So that finishes off one of our cycles. Unfortunately, that's not all 5 numbers. So we still need to look at the other numbers. Let's see what happens to 2 then. And now I'm going to erase my work so that I have space. So 2 gets sent to 4 by the first rightmost cycle. 4 gets sent to 2 by the next cycle over. 2 does not appear in the next cycle over. And 2 is sent to 5. So 2 becomes 5. What happens to 5? 5 is sent to 2 by the first rightmost cycle. 2 is sent to 4 by the next cycle to the left. 4 is not changed, and then 4 is sent back to 2. Process of elimination. We can assume that the remaining element should be a cycle by itself, but you can also check. 3 is sent to 5, 5 stays 5, 5 stays 5, 5 is sent back to 3. So yes, 3 is sent to itself. So this is the answer. Another question I have is compute the order of a permutation. That means exactly what it's supposed to mean for arbitrary groups. It means what is the size of the corresponding cyclic group generated by that permutation. And yes, it is going to take some effort because now you're talking about powers of a permutation. So you got to be able to compute the square, the cube, and so on. And there's usually some shortcuts worth pointing out. So it's worth pointing out a cube is just a square times the previous power. So if you have the square, you can compute the cube like that. Sigma to the fourth power is always sigma squared times sigma squared. So you can always compute the fourth power in a way like that. And so there's shortcuts you can use that you might want to consider. Let me do this example. So this is sigma squared. I can check and see what happens to 1. 1 goes to 2. 2 goes to 3. So 1 goes to 3. 3 goes to 3. 3 goes to 4. 4 goes to 4. 4 goes back to 1. So 3 goes to 1. Likewise, so that's the end of that cycle. There's 6 elements. I only took care of 2, so I need to pick one of the remaining ones. The smallest integer I don't have yet is 2, so let's pick that one. It's worth pointing out this choice is arbitrary. 2 goes to 3, 3 goes to 4, so 2 goes to 4. 4 goes to 4, 4 goes to 1, 1 goes to 2, 2 goes to 4 goes back to 2. All right. Let's see now. So I need to figure out what happens to 5. 5 goes to 6. 6 goes back to 5. 5 is a 1 cycle. Similarly, you can see that 6 is also going to be a 1 cycle. So the order of sigma is going to be greater than 2 because this is not the identity permutation. However, I can see now that sigma to the fourth might be it. Why? Because one thing we haven't taken much advantage of that I could have taken advantage of already here is that disjoint cycles commute. So since the 2,4 doesn't involve any of these elements, I can bring the 2 4s together. Oh, and guess what? 2 4 is its own inverse, so that cancels. Similarly, I can move the 1 3 past the 5 6, so I can get the 1 3s next to each other. And they're also going to cancel, and lo and behold, that's the identity element. So that tells me that the order is at most 4. So all I really need to check then is that sigma 3 is not the identity. And all I need to do there is to just point out what happens to sigma cubed of, say, 1. So just figure out what sigma of sigma squared of 1 is. So sigma squared of 1 is 3. And sigma of 3 is 4, which is not 1. So sigma cubed is not the identity. So by choosing snazzy shortcuts, we managed to, without actually calculating all the elements of this group, we figured out that the order must be 4. And so one thing you can rely on in calculations is that cycles whose elements are disjoint, in other words, the two cycles have no elements in common, commute, and transpositions are their own inverse. These are things you can take advantage of. And if you manage to show that something is the identity element, and you want to prove that other elements, other powers of sigma aren't, it's enough to prove that sigma to the kth power of some element I is not I. In other words, that's just showing that it has some cycle of length greater than 1. Granted, this was a random guess. I could have gotten unlucky. If 1 was a fixed point, I would have gotten egg on my face and I would have had to pick a different number. So that gives some shortcuts for doing the calculations. Of course, nothing stopping you from just computing sigma squared, sigma cubed, sigma to the 4th, using our algorithm that we've already been discussing. And then you should get the exact same results. Although, for some of you, you might have to be prepared to compute all the way up to the 6th power in order to do that.